Okay, good afternoon everyone. So today I'll talk about substitution matrices, and that is part of evolutionary models in bioinformatics. Take a few steps back, let's look at why the problems of alignment, what is the basic problem, and how do we treat that. And today the focus will be on how will we get the substitution probabilities. So if you're just blue-eyed and want to align sequences, you could think, you know what, we just generate all possible alignments and then have some scoring system and pick the best alignment. That might sound like a good idea. And then if you look here, so here you have the mental exercise. If you say, okay, alignment means, say, putting one gap in one of the sequences against the aligning against the other, then how many positions are there? You can place the first gap in front of the sequence, between all the letters, and then following the sequence at the back. So that means there are n plus 1 possibilities. If you then would think, I'll put in a second gap in that sequence, maybe necessary to align it, like here, you can do that then in a total n plus 1 times n possible ways. And this goes on. This will evaluate for two sequences in general. This looks like a simple mathematical formula. It is. It evaluates like this, and in practice this boils down to when you have two mid-sized protein sequences of 300 long, you will have a total of 10 to the power 88 possible alignments, more than the grains of salt on this planet, or sand on the beaches, and so on, and certainly when you go to 1,000 amino acids, big proteins, then this is the number of possible alignments. And think about DNA, sometimes people align 1 million against 1 million, sequences of 1 million long against 1 million long. Forget it. So the trick of, just try them all and score them and pick the best one out of the window. So that is basically why dynamic programming was discovered, it was worked out, was developed, because it cuts down on this combinatorial explosion of all too many possible alignments. It does it, you've already seen that, you've done it on paper, now you're programming it. It does it by breaking a large problem, aligning sequences, up in small problems, because you start at the beginning and all the time you work your way further down, so you align via little subsequences. And that is basically what you do. Basically, without knowing it perhaps, what you're using is you view alignment, you treat it as a Markov process. And the Markov process is about sequential processes that have some kind of memory, and but it's about a series of events. Basically, we take two main assumptions when we do alignment, both of which are biologically probably incorrect, well, certainly incorrect, you might say. And that is, we pretend two things. Sequence positions are totally independent. Any amino acid can basically occur anywhere in the sequence. And also, events, so alignments that happen, that is totally independent. Now, I don't know what you know already, you see it now here. What you know about the protein. I draw protein the last time. Oh, sorry. You know the Pink Panther movie? It was torture. Sorry. Well, this is a protein. I'll do it quickly. Basically what I'm trying to tell you, it has an outside and an inside. And you will find later on, if you don't know yet, that what is inside tends to be hydrophobic, oil-like. So there are roughly 10 of the 20 amino acids have an oil-like character, are hydrophobic. They have a preference for being inside. And let's say outside is mainly hydrophilic. So if you have pieces of sequence that are positioned outside, chances are that they will hold more hydrophilic, water-loving amino acids, right? So it's certainly not true if you look at it that any amino acids will just occur anywhere. There are strict biases. But anyway, that's what we pretend it to be. It makes life simple, and it makes life can be calculated, because you probably know from your school days, when you have two events that are independent, what can you do with each of the probabilities? Multiply them, right? Take the product. So that's great. So basically what we can do, we have this scheme, we can on each aligned position, you can take the probability of that, and then over the whole alignment you just multiply each of those positions, and then you're there. Now there are two things. One, we're lazy. Two is, certainly in the old days, multiplying is sometimes a problem. Certainly in computers, when you multiply numbers, they tend to be small. Probabilities are probably small. What happens if you have a lot of 0.0001 probabilities or something you start multiplying? What happens with the number? So you get 0.00, very small number, and at a certain moment, the computer cannot distinguish between that number and 0 anymore. And it will say 0. And that's of course what you don't want, not a small probability, but certainly not 0. Because then it's over. The alignment has no score. So, because of that, and also because computers were, that's still sometimes the case, are slower at taking products than at summing scores. Some people thought, you know what, from my old school days, I know another thing. What if we take of each of those probabilities just a logarithmic value? Then instead of multiplying all these probabilities, where the number gets smaller and smaller, you just add them up. You don't have a problem. Computers are faster, and you don't get your 0 problem. Underflow, that is called. And the number becomes indistinguishable from 0 in the computer. So basically, log AB equals log A plus log B. You probably learned that in school. So log ABC is log A plus log B plus log C. You can go on forever. So you can just, instead of taking the product of all of these independent probabilities, you can take the sum. Now, if you play it right, if you take the log, then later on, to get the real value, you should of course take the exponent again to convert it back to the real number. But if we're too lazy for that, we just calculate the log space normally. Doesn't matter, because what is large as a log is large in real life, and so on. So, you know, what you prefer as an alignment won't. So normally we don't do that anymore. Yeah? So this is happening since forever, since the first paper coming out about aligning sequences, protein sequences in this case. Okay, so here you go, and here this is what mathematicians make of this. So you call this, and this is the model, independent and identically distributed. So it doesn't, you know, amino acids can occur anywhere in the sequence. There's no bias, and every event, any alignment event, is independent. Not true. And then you have this. Here is the formula, and here there is somewhere a formula in general in the machine. So here's what you do, and here it's said that you don't go, normally do not go back, converting back. Okay, so that's that. So that's great, but what are these probabilities? We need to know about the weights, about these probabilities. So what we do need to know is how do we fill in, and you are already working with that, probably with a Blossom matrix, a Blossom 62 matrix. So hopefully by the end of this lecture, you'll know what that means. So for aligning two protein sequences, you need a set of probability values, call them exchange scores, substitution values, and that for proteins it's 20 by 20. For DNA, as you might know by now, it's 4 by 4. Okay, so, and this is basically what you build up is an evolutionary model in general. Okay, so, what are we going to do? Here is the magic formula again, the recursive formula for each of the cells in your matrix you're calculating as we practiced it last time. You have, for the diagonal steps, that is a match or a mismatch score. You can take a direct value as we practiced last time, but typically these values come from such a matrix, such as Blossom. I just showed you Blossom or same type matrix for DNA sequences. Today on the menu is how the hell do we get the values? How do we get to a model? How do we get a sense of these probabilities? What are they? Is will an alanine like more to stay alanine than a tryptophan likes to stay tryptophan, or is that the other way around? How can we find out about this? What could we use? If we would understand all the physics, then maybe we could do something, but that's what we don't understand, so how can we find out good probability values for exchanges, for mutations? Okay, so there again, we want to fill this matrix with sensible numbers, sensible probabilities. Okay. Well, has anybody already an idea what's the simplest looking matrix you think? What did we basically practice the last time? Well, how would the matrix have looked? We did it for DNA, remember? You remember the model? Match was +1, mismatch was -1. So how would the table look if you would fill in the, you would have 1s on the diagonal and -1s anywhere else, right? And in fact it doesn't make so much difference if you would have 1s on the diagonal and 0s anywhere else. That would work in the same type way. How's that table called, by the way, that matrix? 1s on the diagonal, 0 anywhere else? The identity matrix, absolutely. Very good. Okay. Right, so that would be simple model. But you can imagine that in, you know, when you want to keep track of really the differences between amino acids, all their chemical physical rules, then typically, you know, say the same is one score and not the same is another score is not refined enough. We have to do better. That's what we try and do today. Now, matrices for nucleotide matrices for scoring nucleotide sequence alignment. The probability score, the exchange scores can be simple, as we said, and they're also taken as more. You can use the whole set of different evolutionary models that have been worked out, and I will show you 2 of them to get to some sensible values. Here are 2 models. This is the simple model again. This is the identity matrix. We've talked even the last time already about transversion and transition. Remember the base chemical structure of the bases. But when you change from basic structure, that's called the transversion, and the others are called the transition, purines and pyrimidines. Here are 2 kinds of models. The simplest of the 2 was developed by Jukes and Cantor. Now the Jukes-Cantor model, where you see that basically that it's a simple model that you know, the chance for any nucleotide in this case to change into something else is the same. So any exchange to any other is the same, as you can see here. It's all the same probability alpha. In the model by Kimura, I'll get back to this gentleman, Japanese gentleman, in a moment, you see that there is a difference, that the model distinguishes transversions that are supposed maybe to be a bit more unlikely, a bit harder, because the mutation is from a larger structure to a smaller structure if you have a transversion. So they distinguish 2 values for the transversions and for the transitions, and you can see that here. Yeah? DC, for example, is a transition rather than a transversion. Okay, but still I didn't tell you how these values are being filled in, so we'll do this in a moment. Now, another question we might ask is, what can you do if you want to model it? What can you observe? What can you see? What can you model? So what similarity would you basically expect when you align 2, say, random DNA sequences? So basically, now we go to proteins first, but it doesn't matter. No, nucleotide sequences, sorry. Basically what you get is, and I'll show you a picture I think in a moment, is that you talk about the saturation level. Basically, if you get lots of mutations, you might observe A to T, but it could be that behind the screen a lot has happened, that you have a whole series of mutations that lead up to from A to T because you went via C, mutation to G, and then into T. If you observe a GG, this might just be conservation, as you might, you know, would be the simplest model, but it might have been that there was a mutation to C back into G. This is the beloved back mutation that lots of biologists seem to like. Yeah? Basically what you get is, and I'll show you the 2 plots, that whatever you model in protein sequences, you won't be able to get more than 94% different sequences because of, for these reasons. Back mutations, so a lot is happening. If you model it, you will not be able to all observe it. And the plot looks like this in proteins. So here you have observed sequence distance. So with 94% it means 94% has become different out of 100. 94 positions out of 100 have become different, so only 6 are the same. And you see that the models turn out, they show you that it becomes impossible. This will approximate the 94% level. It will never go over it, it will never even reach it. Yeah? And this is then a model, this is a basic model I'm going to show you later on. Is a model, so in the model it goes on, evolution takes on, the time goes on, and you get more and more mutations over time, but what you really can observe is limited by this distance. Okay? So here you have these two models again that I just showed you, Jukes-Cantor, this one, and this is the Kimura model. Once again, maybe one back. Let's see. Oh no, we go here. Okay. I will also offer this a bit, but to give you a feel of how an evolutionary model over time would work mathematically. Basically, think about DNA for a moment. It's 4 by 4, so this is DNA. You have a probability at a given time for how, what will be the frequency, how many A's, how many C's, how many T's, how many G's will I have, and you can convert that to a probability. So that is here. So you have a 4 vector basically. And now you have this chance matrix for mutations, meaning that this is the letter A. So these are the 4 probabilities for mutation from A into itself and into the 3 other ones. And that for each of the 4 nucleotides you have. Yeah? This is the probability. What is important if you want to calculate between in a small time step, and that is called the rate of change, the transition matrix. And these are sort of probabilities or scores for how fast these mutations are per time step. Now, if you then use this, you can start calculating. Here is what you can use. So this is basically at each, so the probability of the state of a sequence is, here are the frequencies, the chances for how many A's, probability for G, probability for C at a certain given time step, T, and the probability for T. Now here we're going to use this transition matrix, the rate matrix, over a small time step delta t here. So if you would know the situation at time step t, what would be the situation at touch a bit later at the time step t plus delta t. And basically from this rate matrix, I go back to it, that's this one. One thing is that the columns add to 0, so this means that if you add these 3 up, that should together be the same as this one, because you get 0 sum of the columns. And here you see it worked out. That means that the situation at time step t plus delta t equals, of course, the situation at t. And here we talk about what happens in the delta t time step. So you have 3 times that A can go somewhere else, and 1 time, and this is that A stays the same. So this is basically the translation really of what is happening here. You stand yourself in one possible place, and you can go to 3 other ones. The 3 here. And if you write this more mathematically, in continuous time, you see here that the rate matrix comes back in pt plus delta t equals to p times delta t plus the rate matrix times pt times delta t. And if you make it even more mathematically in continuous time, you see basically the same thing. You can see that this relates to here. Again, the change over a small time step is now a differential equation. You get this, I think, in your mathematics class. So then you see that this is a very simple formula to use a rate matrix to get, if you know one situation at one time step, you know it a little bit later on. And what you do here is matrix exponentiation. You get this from this formula. And basically I give you now, I think, the simplest model, Jukes-Cantor, the one I showed you before. Here you have the rate matrix, and you see again here that the chance from any nucleotide to go in another is the same. It's all the same. The diagonal, who can tell me what the diagonal is, should be given. It should sum to 0. What do you think? What about -3/4 times mu? Does that make sense? Good. Okay. I think so. So you find this. I'm asking you this because you find that back a little bit here. This is the exponentiation matrix. This is the solution. This is the integral over that matrix from this formula. Okay, and this works out that there is a rule, and this is often used, that if you have the observed distance, then basically what is the real probability behind the screens? And remember, a model or the real situation, there are more mutations really happening than you can observe. So in fact, you could say the distance between 2 sequences is a bit more than you would observe, right? The model will tell you that. Now, that is like used in this formula. If you calculate, if you plot this formula, that looks just like that, and this is where these curves come from the simple Jones-Cantor model, where you can see according to this model, you will not be able to observe more than 3/4 difference. Yeah? 25% you won't observe. Okay. Yes, Moto, I thought a bit of history. Slotted this in this morning, because Kimura is such a famous guy that I have to give him some credit. He's one of the models. One of the models were Jones-Cantor and the other was Kimura. Moto Kimura, Japanese geneticist, was the first, well, together with 3 Americans who did it independently in the same year, showing you that even, you know, sometimes history is ready to embrace something new. But he is mostly quoted on it. He's the father of the neutral theory of molecular evolution, the neutral theory, neutral evolution. And what does that mean? He basically said, well, Darwin was there telling us that, you know, there is all this selection, and you have these mutations that are normally very bad, and you're sort of selected against, and it's a whole hassle, and a lot of fights, and selection, and survival of the fittest, you know. Well, forget it. Nonsense most of the time. Well, not nonsense, but not as important as it sounded, because most mutations, they don't matter. It doesn't matter. And in fact, if you look at proteins, I already told you something about that. In a protein, you can change 50% of the amino acids without any problem. But of course, you have to know which 50%. So for that, you require a bit of knowledge. But so basically, that is the theory. So difference you observe, Kimura holds, is not so much selection, and so it's more drift and statistical differences. You know, species walking out, you get some other mutations accumulating. Not that they are functionally so important, but just because they're neutral. It can happen. You have always a chance that there are mutations, and in fact, the role of selection is a bit smaller, according to Kimura, than people might have understood from Darwin's words. Yeah? And so, I don't know what to say, what to think about this. There's also what Kimura says. You know. Anyway, the deleterious mutations, so bad mutations, the ones Darwin was on about, you know, are rapidly removed anyway. So they don't change the landscape a lot. You know, they're there, they come up, it's bad, out. You know, over time you won't see much of it, right? And and again, stamping that message down. If they're not deleterious, then most of them will be neutral rather than beneficial. Most is neutral, and that is correct. Okay, but anyway, there was a little intermezzo on Kimura, who comes back at least 2 times, I think. Here you get one example from this simple Jones-Cantor model with this curve I just showed you. Here is a little exercise. If you fill in, for example, you observe, if your observed difference is 30%, meaning 70% remain the same, what happens according to this model? And basically, the distance between the sequences, really, the evolution distance is 0.38. So a bit more, right? You observe 0.3 difference, but you might say what has really happened with back mutation is quite a bit more. So the sequences are really a bit more different according to the model than you would observe. Yeah? So you might say, hey, if I trust this model, maybe it's good to build this in your alignment scores, right? Correct them according to such a model. Okay, here, Kimura, according to Kimura's model, remember that model was with transversions and transitions, so here's a little example where we say it's again 0.3 difference, but now we say, okay, 30% different, 20% is due to transitions, and 10% is due to transversions. Just one example, and if you fill that in the Kimura model here, then you get this score, and, you know, starting with 0.3% difference, relative to these two, Kimura even says, no, the real difference according to my model is even a bit more, 0.4. Here it was still 0.38, and now according to this model, it's now 0.4. If you start with 0.3 in this mix, okay? So meaning these models do matter if you're interested in real, whatever that means, differences between sequences within a sequence family. Okay? Now, this was all for DNA. Here you see again Kimura, which is very active. Developed a model for proteins as well. You should try and calculate, fill in some values, then you find out that's a bit of a crazy model. But if you fill in again, you know, 0.3 as in the other models, and this is now for protein sequences, 20 amino acids rather than 4 nucleotides, but you get the exact same outcome as in the Gibbs-Cantor model a moment ago. But look what happens if you go to a little bit more differences, 50% difference, then the model will predict 0.80 as the real difference according to this model. So quite a difference between 50.5 and 0.8. A little problem is that it's pretty heuristic formula. That's a nice way of saying mathematically it's crazy. So it's heuristic. Mathematics of course call this crazy. But then biologists say, well, we can calculate with it. We learn something. We don't care. We're not so faint-hearted, you know. So anyway, but you can try this on your calculator. If you go to this type of then this, you can't calculate it anymore. You get differences over 1 or below 0. But again, a biologist, they don't matter. I will show you later on in my lecture on phylogeny that there are cluster methods that work with distances that are negative. Some mathematicians are opposed to this idea, but biologists like anything in life, right? They take life as it comes, you know. Anyway, are there other models? You bet. There are bookshelves. This whole room could be filled with books on all of these different models, you know, because it's mathematically pleasing. You learn a lot about it, but in practice, in molecular biology or in the alignment business, most of these models, most of these so-called corrections by models are not used. There's one program that's obsolete now, Clustal W, who used Kimura correction for the proteins to make phylogenetic trees of the sequences. But that program is not functional anymore. There is the next one, which I'll talk about in a few in 2 lectures time, I think. Okay, so that's basically on all of these models. Yeah, so they can be used to correct and to get, but the important observation is, again I use the same word observation, what you observe in terms of mutations does not straight reflect what really happens, because of all of those indirect mutations, A via something else to C, and back mutations. Okay? Okay, now back to how can we fill a matrix with 20 exchange scores for protein sequences or 4x4 exchange scores for DNA sequences. Now, if you compare quickly, looking at DNA or protein, suppose you have sets of DNA sequences and you have protein sequences that are derived from those. What is better to align? So here are a few considerations for you. When you align DNA sequences, you will align synonymous mutations. Do you still remember what that meant? Mutations that do not change the protein sequence, as well as non-synonymous mutations, mutations that do change the protein sequence. So when you have many synonymous mutations, DNA will say, ooh, we are quite different now. And the protein sequences say, I don't sense them, I don't see them. So you overestimate divergence, so differences, if you align at the DNA level. What is else? What more do we have? Okay, so you know already, we talk about a 20 by 20 amino acid exchange table for proteins, while for DNA you have 4 by 4. So some people say the 20 by 20 table is more expressive. You can more fine-grained put in differences. And that's another reason arguing for the fact that if you have the option, align at the protein level. DNA sequences contain non-coding regions. Well, there Kimura gets, of course, absolutely his way. It's not only neutral evolution, but even, there's no functional selection on here. So this is just drift. And that means you get easy accumulation of differences that looks all dramatic, but has no functional consequence. So maybe you're overemphasizing differences if you do that. Yeah, okay, if you have, one point, of course, is if you start with DNA sequences, and you need to make protein sequences out of that. I've shown you, I think, a translation table. But then you need to know something that is called the frame. I don't know if everybody's aware of that, so I'll quickly fill you in on this. Here you see a frame. Basically 3 letters are there to really encode an amino acid that is being encoded by the DNA. And you could have a frame like this. ATT, if this is a DNA sequence, the frame could be like this, but as I think I already showed you, you could shift the frame, so you could say the first frame is TTC, then I get GTT, and then I get GGC, and so on. There's this frame, and you can do it once again, then the frame would be TCG, TTG, and so on. So what happens if you shift once again? then you pay, of course, the square one, the original one. So that means if you have a DNA sequence, in this direction of the sequence, you have 3 possible ways of making a protein out of it. But you know, a DNA is a double helix, it's double-stranded. So you have if this is the plus strand, you have the minus, the complementary strand. And there you can translate into 3 possible protein sequences. Once again. So that means if you have one stretch of DNA, there are 6 different protein sequences that you could conceptually have encoded by that bit of DNA. Right? In practice, in biological systems, it will be only one in most cases. Although there are some sequences, there are very smart organisms on this planet, such as bacteria and viruses. Is a virus an organism? I'm not going to ASA and discuss that now. But anyway, they have one big restriction: their DNA is very small. So that they need to pack a lot of information in little sequence space, you might say. What do they do? Very clever things, double coding. They say this bit is then for this protein, and then they start here, the same bit of sequence, but do it in another frame, and you get another protein, but that one is also functional. So I'm not telling you that it never happens, but it's relatively rare. But organisms can be very clever when it comes to coding. Anything a computer scientist has ever dreamt of before, you will find in a biological system. 4.2 years of evolution is a bit of time to think, to get some good ideas, basically. Okay, anyway, about the translation problem. You might say that this may be against protein, because if you do this wrong, you will, of course, align with incorrect protein sequence. That's not a good idea. So frame shifts are dangerous, you might say, but then again, here you get an example of a small frame shift. And what do you normally see? If you have a protein family, then a sequence that accumulates a frame shift you will recognize immediately. It looks like nothing. So if you do a frame shift, the amino acids you get as a result are way different. The sequences are totally dissimilar. So you will immediately pick it up like there's something strange happening with this sequence if you have some others that are supposed to be family, right? Really the odd one out. But normally, as is already suggested here, it was called a nonsense mutation. The chances are there that if you have a frame shift, that you get very soon a premature stop codon. That is not really there. Okay, but anyway, rule of thumb, if you have an open reading frame, that is a stretch of DNA where you suspect that a protein might be encoded by that stretch of DNA, then it's a good idea to at least try and align at the protein level, also because you're closer to functionality. The proteins are the doers in the body. They perform the task that is encoded in the DNA. And again, so scoring, yeah, on scoring. So now, how are we going to, this is for DNA, and here we have the 20 amino acids for proteins, and you see they can be categorized. Some are, have all kinds of rings here. These, they have different, some like water, some are polar, so these ones, they like water, they're basic. You have all kinds of characterizations of these amino acids. And here you have an odd one out who knows something about what's funny about protein. Who knows? Any chemist here? Okay. Normally a protein looks like beads on a string. This is a protein. You have a piece of main chain. Who's worked so far? Well, sorry. It's just to wake you up, okay? Sorry, this end. Maybe that's better. So, this is a protein. Main chain bit and side chain. In Dutch, bedeltjesketting, how would that translate into beads on a string? Is there any chain that has this? Native speaker, or is that called in English? If you bracelet like that, these bracelets that look like this. Do they have a name?
Necklace?
Yeah, necklace. Yeah. I'm there, yeah. Okay, anyway, I thought so. I don't know the English name. Maybe there is none. Okay. And what is Dutch is more cultural. Okay. Anyway, and but this means that the main chain is in a way independent from the side chain. And proline is a funny thing because what it does, it binds back to the main chain, and therefore imposes some corner, some angle in the main chain. So in that sense, it interferes with how the main chain folds. It interferes with how the protein can fold. So it restricts it. And that makes a protein very special, and that's why it's really found in specific places in the meat. Okay, just a bit of side information. Now, basically what I'm trying to say to you, this is sort of a complex world with all of these amino acids. They can be physiochemically different. The likelihoods where they might occur can be different. But there is one rule: if you are going to change a protein structure by changing amino acids in the sequence, you will have an easier life if you change these amino acids to other amino acids that are closer to it, nearer to it, that are more similar to it in the physiochemical sense, or maybe therefore in an evolutionary sense. To change a glycine, the smallest one on the planet, into a tryptophan, the largest one on the planet, suppose you'd like to do this here in the protein. One little piece of information for you: the protein core is so-called densely packed. There is no space. All the atoms are at a distance. There are no holes in there, right? So now you say, okay, let's make the smallest one into a very big one. Let's change a mouse into an elephant. What's going to happen in this core, you think? The elephant knows what to do. It's a very strong animal, right? That means the protein has to change its total configuration. That means chances are that the beast will work differently after this mutation than it did before. Normally it won't work anymore. So that is, of course, even though Kimura said most is negative or most is neutral, this might work out negatively. Right? Bad for the organism, bad for fitness. There you go. Less chance for it to happen. This is the famous Taylor diagram. I was in London, no, not at the time, but he really was my boss for a while. And he made this splendid diagram showing about some possible double roles. These are the 20 amino acids. And here you see all kinds of classes there. So you have a hydrophobic bunch, you have hydrophilic, but then within hydrophobic you have aliphatic. There are small amino acids. Are there big ones as well? No, only tiny ones. Small, not big. That means not tiny or not small. It means big, I guess. And so this is sort of a nice overview of what amino acids could do. Let's look at arginine. It's positively charged. And what else it is? It is charged. And it's polar. Is it something? It's just outside. What's this one? The hydrophobic ones. Then I like the lysine example more. It's also polar, but lysine can also case for lysine. Sorry about that. 20 letters to be given out to amino acids. But lysine is also hydrophobic. Yeah? So some amino acids can play a double role. They have a polar tip and then a long apolar tail, so they can use that and behave like apolar, or use the tip, so they can do different things. This is sort of hopefully reflected to somewhat in this Venn diagram. Okay. This is about other things that can happen. Just a few examples that in the protein world things happen. Smaller proteins very often. If you have a big protein, then it has an outside, but it has a well-defined hydrophobic core. With lots of hydrophobic amino acids, so it's a big football, and so there is stability there. If proteins become very small, there is hardly an inside anymore. Water can almost get anywhere. And those proteins are typically less stable. And if they have a need to become stable, they call rescue teams. And there are two ways. That can be with cysteines. Who knows what can happen between cysteines? Cysteine bond, Slavelbrug in Dutch, right? And salt bridge, also called. And that's really a bond between two cysteines that it really can stabilize the protein structure. Another thing that proteins can do is they recruit some metal, in this case a zinc ion, and then you have these amino acids that sort of interact with the zinc ion based on electrical differences, you might say, and that also, so these 4 amino acids are now sort of stably bound together or held together by this interaction. Yeah? So small proteins need this sometimes to gain stability. Right? Question? Yeah?
What do you mean to reducing environment?
Say that again?
Reducing environment for the system?
Yeah, they happen in some, absolutely. They happen only outside the cell, for example. Yeah, that's true. So all of these things do not just happen anywhere. That's true. Absolutely. Good point. Yeah. So, nice sort of DNA binding protein is a zinc finger. And the hallmark of zinc fingers, as the name implies, is having zinc on board, right? So they use it. Okay, now we go into really thinking about algorithms. Basically what we're going to do, we make a simple model and see how could we get an idea of how can we get to probabilities and to exchange probabilities and all that. So basically we're going to think about simple alignments, ungapped alignments, gaps, that is gap penalties, extra complication, let's forget it for a moment. Let's only have alignments with matches and mismatches, and no gaps, then you can think more easily about it. So you have two sequences, right, and a net. So, if you have such a problem, and this is sort of general advice to you, if you have a problem and you need a mathematical formula, you don't know quite what to do, the best thing you could do is talk to a statistician. Who knows about statistics? Let's talk. Can you help me? So if you do that, you almost always get the same answer from such a person. And that is, you know what, I know what you need. You need a zero model. You need something to offset, what you see, how statistically significant is that. So you need to compare it against some reference. Let's call it a null model. You need a null model. So you, being an evolutionary biologist at this moment, you say, okay, so I want to really have scores, my model, really substitution scores, the real ones, please. So how could I get to a null model? And then the statistician will again advise you and say, well, think about a random situation. What would you randomly expect? And then you can compare your model to random and you can see how different it is and how important it is. Okay, so that's the plan. And as I already said, basically we will use logarithmic values because we're going to add up values. But anyway, basically, according to the statistician, we should be interested in the ratio of the values given by a model and compare those, divide those by those, the same equivalent values but generated by some random model, random situation. Okay, so let's first think about a random situation. And we do it in a very simple way. We have the IID problem, independent, identically distributed, right? Any position, anything can be, and there is no relationship between positions. So then, if you know nothing, look only at these two sequences. How likely would you say it is that an A will be aligned on a V? Remember, they could occur anywhere in the sequence. What would you take? Anything? Any idea? It's early in the week, I know, but it's already afternoon, right? You've woken up by now. So, who has an idea? I'll throw one word in, okay? Frequency. If this sequence would be totally A, and this sequence would be totally V, how likely is it that an A gets aligned to a V? Pretty likely, right? Let's say 100%. Why is that? What's the frequency of each of them? 1 and 1, right? If you multiply those numbers, what do you get? 1. Fantastic, that's the answer. Now, so what would you now say, having heard this limit case about, so what's the frequency of this amino acid? Could be anywhere. So let's say 50% A in the top sequence. What about the letter V in the bottom sequence? 50%. So what would you then say? Them being in register, falling on top of one another, what's the chance? And the statistician will tell you, if you ask again, 0.5 times 0.5, a quarter, right? So that's great then. So that means this one is a quarter chance. We score that as a quarter. This one we score as a quarter. How would we score this one under this scenario? I'll tell you, 1/4 times 1/4 perhaps. And this one, same. Hey, that's great. We have a random model. We can fill in, we can score each aligned position according to the simple model and get a value. Now, you have heard in school probably or during your bachelor program about the sigma sign, adding up a lot of stuff. You know this one? This is the equivalent, no not equivalent, it's the same thing as, this is the sigma sign for taking the product. Yeah? This means, you multiply all of these letters. So basically that's what we just did. What do you say? The alignment is basically 0.5 times 0.5, 0.5 times 0.5, 0.25 times 0.25. So they do it like that. But they just multiply all those numbers and that gives you the random, the score, the alignment score according to a random number. Yeah? Just based on the frequencies in the sequence. So we have our R model, and we are half there now, right? We have this one, nice and easy. Now this one. What can we do here? Well, does this really help? We say, given what we need is now in the real model, the M is we need a probability for AV, the real one, right? And one for this, and one for this, and one for this, and at this moment we don't know. So if you don't know, you give something a name, and you put it on a piece of paper and try and forget about it. This won't work now, because we have to get to this model. So basically we don't know. This we know, we don't know that. We need to think a bit more for that. So we talk about the real model is called the target frequencies. What is really happening, and we have background frequencies. These are these frequencies we just calculated. Yeah? And for real frequencies in databases, you need, of course, trusted data sets. Yeah? You need some protein sequences. You want to get a hang of what could you randomly expect in sequences, in many sequences. You need a good representation of the sequence world. So you should not select some crazy sequences and then calculate. You should have a good average view of what you would expect. So that is what we try and have as well. So I already told you this trick. Lazy, not getting to underflow problems. We tend to logarithmize the scores and then take the log of the scores and then add the numbers up. So basically that means, that's sort of easy, if we do that, we convert this formula into a logarithmic score. What can you do? Instead of taking ratio, you subtract, you take minus. So makes it a little bit easier. That's here. Basically then you're on about target minus the background, which is the ratio in the log world. Okay, so now we write, it looks already very complicated, but we've done all of this, and still, we are still cheating on the real model, because this is just these probabilities we still need to find, right? I'm not off your hook. I still have to come as a sensible answer there. These ones are not known. The random frequencies we now know. And if you go to a log odd world, all you do is take the log of all of this, it's here, and then you get nicely subscribed. Instead of all these products, you now convert to adding up all these log scores and then you know, right? This is the formula base. And this is the exact same thing here, but now you've converted everything to the log world, as we said we would do. Okay, now if you have a log score, what does that mean? That means if what happens to a log when the score out, when this ratio is positive, is larger than 0, you get of course a positive score, right? You mean which log is always 0? Evaluates to 0. Log what is 0?
1.
No, not 1. So that means this is 1, meaning the model is exactly the same. The real model is exactly the same score as that of the random model. You get 0. So a positive score means M larger than R, 0 means the same, and negative means R larger than M. Right? So we balance, we can see, but we look around 0 scores. Okay, so this is just saying it again, what we just said, and this is for each of those scores, the exact same thing. So we're still on, here we have these frequencies we know about, and this score, the real score, the real sense of mutation probabilities is still not there, we need to find it. Now, this is what you know now, in the log scoring. What do? Everything is independent, so you take the score of that one, and you can see this is not a gapless alignment, so basically this is really what we do. We do something special for those funny positions with gaps, and we've already talked about linear gap penalties, and affine gap penalties, and even concave gap penalties, right? Okay, now here's already part of the ID. If you don't have a great physical ID of some godly ID, what do? You look at the world. What have we got in our hands? What can we observe? Can we derive something from that? And here's one of the ideas. What can we do? We have a lot of globin sequences or hemoglobin sequences. Maybe we have already lots of alignments. Maybe you have already a good idea from all kinds of alignments where biologists say, hey, this is really what should be on top. This is a mutation. We see very often a mutation from A to V. And we hardly see a mutation from W to L. So, if you observe that, can we do something with that? That's the idea. Well, basically, To cut a long story short, in this sense, there are two main matrices, series of matrices. This word you've already seen. You've already heard about the number following it. I think also 62 is probably known by you at this stage. I'll tell you more about that in a moment. So I'm going to focus on these two matrices series. The first one, this is my champion in bioinformatics. For me, this lady is the first real bioinformatician. She died all too young for cancer, but she wrote one book, and that is The Atlas of Protein Structure in 1978, and it still reads like something very modern. This has not become moved by time. It's fantastic. If you start reading it, you will be astounded by, wow, this is like today. It's very good. It was a visionary. So she lived in the time when there were no alignments. So 68, the first suggested algorithm was in 1970. All the work she did was in the time when there was paper and a pen and a telephone. Right? That was the only thing. No email, guys, sorry. No, nothing. No app. Nothing. So, she had to collect, and she had this idea, I should find sequences. I need to work out some likely scores for mutation. You know what? I'll ask my colleagues over the world whether they have protein sequences. And then I'll think on what I get as a database. So she started writing paper mail letters, 3 weeks delivery time from America to the UK, for example. Dear colleague, I hear you have a globin sequence. Would you care sending it to me? And then, 3 months later or so, a letter came with a handwritten protein sequences with filled pen, already, totally wiped. And of course, 3 errors per 200 at least, because a human writing something means error. So that was her. And from that she had an idea, if I could make some alignments of families, these sequences, how should she do this? By hand, because there were no alignment routines. Then I have some empirical evidence that I could look at and maybe get a good idea about these probabilities. So, here is what she in the end constructed. So she used here, look at this. This looks like data, you're laughing about it. She collected 71 families of protein sequences. But that she did through paper letters. Dear colleague, would you have a sequence from me? Yeah. And then she collected a family of 10 sequences. Wow, 10 letters, 13 time, or 20 sequences. Nowadays we have thousands in a family, we don't know how to stuff. Anyway, so 71 families, amazing. I don't want to tell you about the error rate in each of those sequences, but anyway. From that, she was the first to extract really a 20 by 20 target matrix, so with the PIJs in it, right? According to this crappy set of sequences, of course. Now, she was in a way lucky. What do you do if you want to make alignments? You have long sequence. You look, how do you do this? By eye. You think it's easy? What about aligning an identical sequence? Difficult? Easy, right? What about aligning 1 in 1,000 letters different? Like DNA. It's easy, right? Basically. It's all the same, so this one must fall here, and then I'm in register again. But what if you get sequences that are 50% different? Forget it, it's hell. Yeah? Okay, should I tell this at this point of time? Okay, I'll tell you what one of the geniuses that I know about. I know 3 real geniuses, astounding people. One of which was a Brazilian gentleman. I've never met him. He died in the meantime, I've been told. Can't check out where he's still. And he could do multiple alignment. I'm going to give a lecture on multiple alignment. 50 sequences, 500 amino acids he could do off the top of his head. And I don't know how do people do that. Well, sometimes people tell me you use a piece of paper. Okay. I don't know. Some people have that, right? Probably the only thing he could do. Probably a terrible guy, I hope. It would be terrible for all the rest in his life because there would be some sense of balance, right? But I can't check because of that. Anyway. So basically, let's go back to the PAN model by Margaret Dayhoff. So basically, a 20 by 20 table, and you need to fill each of those values with some sensible probability for a mutation, including on the diagonal the self-mutations or the self-conservations, yeah? Letters remaining what they are. Now, she made a fairly complicated model, certainly given the date she had, because she was in the age where phylogeny was just coming up and everybody thought about making trees, so she also thought about making trees. And so she was reasoning, well, what I should do if we have, for example, this sequence, And this sequence, and I align them so they're homologous. They must be homologous. And what's the definition of homology? Having a common ancestor. So she even took the trouble to construct the most likely common ancestor. Reasoning back in time, right? So if you have IT, you have a problem. Should maybe I or T, that's the letter here. You pick this one. I is maybe easy, right? Then your likely guess is it was I also in the ancestor, and so on. So she did all of this reasoning to extract from the sequences that are there at the current time, the present time, all of these theoretical ancestral sequences. Okay? And from that she took the mutations, stating that if you have this example here, for example, here, that means if we have this ancestral sequence T, then you know what happened if you go to the sequence D, the descending sequence. What happened here? Apparently a mutation from the letter T into I, right? And here, what happens here, this was T to T, was the first mutation here, K, L, L, oh, no mutation. Everything remained nicely the same here. But not for this, just one example, okay? So she extracted, she started counting from all of those data sets where she made the alignments by hand, but she was lucky, I forgot to tell you, because her sequences were 80% or more similar. So it worked, so she had not really a big alignment problem. She didn't need the Brazilian guy, maybe he was too young by then. But anyway, she could do it, even Mark. But Mark was pretty smart too, by the way. But she could also do alignments very good, very well, off the top of her head. Anyway, she did. So this is what she used. Basically, this might surprise you, at the same time she said, you know, yes, doing it now, right? Yeah. Yeah, okay, thanks. Was this just happened, or you're really trying to get my attention for the last 15 minutes? Anyway, okay, so this is just what is here. Oh, and there are two things. If you say how many did mutate away, that is 8 divided by 8 plus 1, right? And how many mutated away? You might say that is 1 minus the fraction that remained the same, right? Yeah, because that is 2 divided by 10. 80% remained the same, and that means 20% started mutating, right? That's what you see here. This is remaining the same here, HJJ, fraction remaining the same, and 1 minus the fraction remaining the same equals the fraction changing, but you can also calculate this straight by adding up. And how did we do this in this matrix? Sorry. What do you say if you want the guys that mutated? These are the off-diagonal elements, so that's this one and this one. You add them up and divide it by 10. That's basically all this horror here is that. Okay. These elements where I is not J and not A, the first position. So this is exactly what we just did in the toy matrix, right? Okay, now this is just to give you a feel. You do all of this and you normalize this with the value for alanine. You set that to a value of 100. Here you get the feel what amino acids tries to mutate a lot and which amino acids do not want to mutate. What is the smallest number? Did I check it? I don't know. I hope. Look at TRP. I saw it already. Did I tell you about tryptophan? It was the largest amino acids on the planet. Maybe there are some constraints there if you change. So you see here, according even to the day of model, tryptophan is unwilling to mutate. It tries to remain the same. Okay, so this is this, and this is the probability. Okay, if you have to go back to this matrix, very simple. How can I calculate from this matrix what's the frequency? How many A's are in there? How many B's are in there? Not mutations, just the number of letters. What you can do is you take a column sum or a row sum, doesn't matter, and divide it by all the numbers in the matrix. That gives you, because of this table, the number for so 8 divided by all these numbers added is the frequency for A, and so on for each of them. So that is basically what we see here. It's just for each of the letters, each of the 20 letters, PJ, you do this matrix calculation, you have just the bare frequency. Now we have two things. We have the so-called, I didn't say, but this letter, this means the mutability. What fraction of an amino acid wants to mutate away into whatever different letter? That's one thing we calculated now. Here we have this other thing, just the frequency of that amino acid. the random chance for it being there. And if you multiply those two things, the mutability times this frequency, the base probability, then you have the total mutation rate of that amino acid. And if you add everything up, all 20 types, you get the total mutation rate over all amino acids. Yeah. The calculation step. So basically, given this set of alignments, she extracted one number that said how much of the stuff wants to drift away from what it was. Whatever the letters, doesn't matter. What's the overall greed at mutating, you might say. And then she said, you know what, now I want to put a number on that. I want to scale that to 1 in 100, just a choice. Could it be 1 in a million? Could it be anything? But she chose 1%. So she says, okay, what I'll do is I'll scale this, I put a lambda scaling value in front of this, and I say lambda times this number, whatever it is, should be 1 in 100. And if you do that, you have this number there, you have 1 in 100 here, then you can calculate lambda easily. So she had a scaling value. Now we are getting somewhere, because now we start filling in basically numbers of the matrix. We discern two things, the letters that mutate away and the letters that remain the same. So Mij, where I is unequal to j, so this j changing into I, is this formula now, with this lambda scaling value now calculated, and remaining the same evaluates to this little formula that is just 1 minus this. Because if you stay the same, it's the other flip of the coin by mutating, as we already said. So here is that matrix that comes out of that. This matrix is not symmetrical, but this adds up like this to 1. If you add these numbers up, you get 10,000. Yeah, this is the Dehoff's matrix, and you see in those days everything was cumbersome. There were no printers, there were only plotters. And she said, you know what, I want to put 0.9867 here, below 1, but you know, this is a point and so on, takes too much space, cannot put it on a paper anymore. You know what, I'll multiply everything by 10,000. So this means 0.9867. And this means 0.0001, I think. Yeah. And so on. So what do you see if you look at tryptophan again? Ah, it's the letter W, sorry. A single letter for trip. W, look at it. What's the highest diagonal value? The closest to 0 to 1. What do you see? It's the winner, eh? 9976. It is the winner. Should be the winner. And which amino acid does want to go away the most? What's the lowest number here? I don't know. Lysine, perhaps. Alanine, maybe. 98. No. It's lower. 97? No, big guy. And in her book. Okay. So what have you got now? She has basically said she called this the PAM1 matrix, meaning this is the probabilities given a model where over whatever period of time 1 in 100 amino acids will change, will mutate. 1 in 100. These are the probabilities because of that lambda scaling factor, okay? So 1 in 100, and then she picked. In a few minutes I'll break up anyway. So yeah. So basically, sometimes the urge is just too big. So basically, she started reasoning, and I tell you already one thing. She fixed a period on that, and she said 1 million years. 1% happens in 1 million years. And now the point is, how do you get to 2 million years? Anybody? You know what? Think about it over the break. Because otherwise I'll keep you reading for too long without coffee. Could that happen? There's already a hint at the bottom. Now put it on. Nah. No, let's do it anyway. On pause, right?
Yeah.
Being stern, so it's good. Okay. Right. So the question was, if you have a matrix for 1 million years, how could you use that to cover 2 million years? And there is maybe one main realization: 2 million years is twice as long as 1 million years. So if your assumption is what really happens, the chance for something to happen in the first period is basically the same chance of that to happen in the second period, then you can do something. Now let's reason a little bit about that. So what have we got? We know these rules, so Dayhoff took, this is just a little rule that x to y is the same as y to x. We covered that. This can happen x via z to y, and that's a nice thing to have here. Everything's Markov. This is just a slide about the basic assumptions. But here is what I would like to tell you. If you have two periods of PAM1, 2 times 1 period of a million, then what could have happened if you have over 2 periods A to R, how could it have come about? Well, here for example, in the first period A remained A, but then went into R, or in the first period A went to N, and then N went to R. These are all possible ways of mutating A into R, right? By all these in-between steps. So, basically, all these probabilities add up to the likelihood for this mutation, right? These are all possible scenarios to mutate an A into R over 2 periods. Now, if you do that, and you want to calculate that, then you have all of these things that you should multiply, and basically, if you do this, you talk about all of these chances, 1 period, second period, AA and then AR is A to R, AN and R is A to R, ADDR is A to R, and so on and so forth. You add those all up, then you have your probability. But what do you do mathematically if you do that? That's basically this. It's beautiful, right? Matrix multiplication. Do you know how that works? If you don't, look it up. Yeah, it's, the result is sort of this times that for each of the columns. And that's exactly what we need here. So now my question is, what then if we want to go over 3 periods? What will we do? We have the 2 already, that's this. So how could we make a 3 period from this? Well, here is already the suggestion, of course. Then you would do matrix multiplication 3 times, m times m times m, and typically for all possible periods, k, combination of periods, you do the matrix multiplication k times, right? Just k times this matrix multiplication. And then you are there. So basically what we have is, you have the PEM unit calculated by Dayhoff, all these dear colleague letters and the protein structures and the families and the handmade alignments and then the counting, making the tree, the counting, all these calculations using the matrix to the PEM1 scores. She can now extrapolate those scores into any evolutionary period, 1 million, 2 million, 3 years, to 250 million, 500 million, whatever you like. And the number she put reflects that period. So she has now a series of matrices, basically. She created. And here you go, this is this visually. You self-multiply a matrix n times to make a PEM n, meaning n times a million periods. Yeah? So it's a PEM is a relative measure then of evolutionary distance. Yeah? So 1 PEM again is 1 accepted mutation per 100 amino acids. Point accepted mutation is the meaning of PEM. Horrible name, but hey, there you go. And 250 PEM means 250 mutations per 100 amino acids. So if you do this, and you say we do the period 250 times, PEM1 means 1 in 100, 250 times that means, on average, 2.5 times. So every position in the sequence changed 2.5 times. That's quite some evolution, right? You can do a lot if you do that. Okay, anyway. So basically we're nearly done with all these calculations. So this is the self-multiplications, and now she needs to really convert to the log scores, and that happens like this. I showed you this matrix. Do you remember I told you this matrix is not yet symmetrical? Only the columns add up to 1 and not the rows. So now after this the matrix has become symmetrical, and that is what you want in the end. So basically Dayhoff matrix is here, and it's now a symmetric matrix. Okay. Now, I'll show you the matrix in a moment, what the numbers are, the log odds, so the numbers converted to a logarithmic scale. And here you see what these numbers mean, the PEM number. PEM1, what was that again? 1% accepted mutation, meaning 1% mutated, 99, the same. So a PEM 250 is the most widely used PEM matrix, I can tell you, means 80% mutated away, 20% the same. It's quite some mutations. 80% is gone. It's something else. That's this model. And you see, you know, well, of course, what you expect, the longer the evolutionary period you take, the more you expect that you get mutations away from your base type or the type you started with. Yeah? Right, here's the famous PAM250 matrix. So what do you see? This is logarithmic score. What did that mean again? 0 meant just compared to random, the same. Positive means more than you would expect against the random model, and negative means less than you would expect. And what do you typically see? The highest values. You know, mathematicians, they have to vomit when they see this. Again, it's biology against mathematics, right? Why is that? I call this matrix not well behaved, terribly badly behaving, basically. Why is that? Because this is a so-called similarity matrix. And what this matrix says is that a tryptophan is 17 itself, right? While an Nesson is only 2 times, you know, the same. So going from N in N is 2 points, and from W into W, 17 points. So you're the same or you're not the same, according to a mathematician, right? And here that's not the case. So again, biologists say, yes, that's another possibility of doing it mathematically correctly or well behaved. We like to do it like this. Because we can now do alignments in here. You can use this matrix and fill in the scores now. And add them up and have your alignment score. Now, if you look, and this is the tryptophan here, and according to biochemists, and always trust biochemists of course, if you look at the type, at the chemical formula, then it's very surprising that the tryptophan, this is +2, right? You see, tryptophan doesn't want to mutate. Everything is negative. Almost everything. 0 here, okay. The rest is all negative. See, it doesn't want this less than you would expect. And here it wants +2. An amino acid that has nothing to do with the tryptophan. Who has an idea how could that have come about? Terrible error in the matrix, so warning. And Dave will tell you, I did it exactly right. All my colleagues checked. You know, no errors in the mathematics. I took the data, and this is what got. And then you say, yeah, that's what I mean, the data. What do you think? What was wrong with the data? Write it down. Write it down is one thing. But what about the size of the data? Extremely small. So could you have a chance of a funny situation that there are a few RW mutations in the alignments that are overrepresented because it's such a small database? You get it, right? So this is just the artifact of the paucity, the fact that the data set is so small. Yeah? You know what? Now this is now I fill you in on something very scientific, right? Anybody knew this after a few years? This has been done, this exercise, with far greater data sets. The Thornton-Taylor JTT method. New matrix updated. Nobody uses it. Why? People say, well, I'm used to this. My algorithm already corrects the 2. So if I use the proper matrix, this all goes wrong. I don't want to change. You know, it's as if scientists are also people, right? That's basically the message. Amazing. And that happens a lot. And so that's the famous error in the PAM250 matrix. It's not an error. It's, they often call it a feature. It's just a result of the data set, right? Okay. Yeah, all of this we had before. So, this of course you can see now. How can you use this? A disruptive substitution is less likely to be selected. How would we find a disruptive substitution? One that scores fairly negative here, of course. Right? These are the things that do that. So, and how do we score this? How do we take these scores? How do you take these scores in your alignments? You add these numbers up, right? So, what do you get if you get all kinds of matches that are these numbers? Your score is low. So that alignment will not be selected by the dynamic programming alignment. It guarantees the high scoring out of very many. Okay, so that's this. So basically, that's what's here. This is just an entirely empirical approach. The numbers they have got is just by you're looking at the data set. There's no physics there. It's just what did I observe? A bit of massaging, and then you have something. Okay, so basically this is already what I told you. PAM1 is a million years. PAM120 therefore is, that's another point. PAM250 is the most widely used matrix. For some reason, it's 2.5 expected mutation per position. Then some mathematicians started, the man who wrote basically was the inventor of the Blossom algorithm. Blossom algorithm, the BLAST algorithm. Anybody? BLAST? Yeah? No? No? Oh, okay. Anyway. And he said, you know, overall, people should use PAM 120. It has the greatest information content. So, world, use PAM 120. Here is the proof. My paper. What do people say? Steve Altschuler it was. Yeah, Steve, you're a nice guy. We're all used to using PAM 250 now. So. Very nice paper. Congratulations on it. But PAM 250 is our thing still. So, PAM 120, hardly made it. You can check in how many algorithms if you click. Oh, you could check Praline. I think he put it in. But the click buttons might not even have the PAM 120. You could check sometimes. All right, so here we have a summary of the day of PAM matches. They're derived from global alignments, just 71. Pretty similar sequences, aligned by hand, but globally, right? Then you will get a base set of frequencies covering 1 million years, PAM1. And you extrapolate those matrices for longer evolutionary times, larger evolutionary distances. So this number is just the number of cell multiplications, right? 40 cell multiplications, 100 cell multiplications, right? Okay, and here are these other, you know, these updates on the matrix. Conner and John Thornton, they all did it quite a bit later, a while ago again. Nobody ever used this stuff in large measures. So after this, people said, well, we could try again to update it once again. But nobody will listen anyway. So this is sort of that business. So that's it, PAM 250. Okay, very simple rehack. You Blast work with the Blossom 62 matrix. You are probably working mostly with the Blossom 62 matrix. So you might want to find out how that came about. It's much simpler than Deof, I can tell you. Same type calculation, but many times simpler. Yes?
But if we keep updating those matrices and make them better, why did nobody use them? Because you would probably get it better alignment.
Yeah.
Yeah,
you tell me, I don't know.
Okay.
You know what I found, you can even make, I shouldn't say this, even if you make errors in your dynamic programming routine, the alignments are normally not even so bad. So in that sense it's error tolerant, you know. The autograder will be very stern with you anyway, but actually biologists could still work with it, and even they might find out in 5 years, hey, this alignment is really strange. And then they come to you and say, oh bloody hell, big bug in my program, I'm sorry. But you know, not always really lost in those cases. Anyway, let's quickly do the Blossom series. How much time is there? 10 minutes. Blocks, the Blossom matrix stands for block substitution matrices. So, where the Deof philosophy was, you take the alignments, you align them globally, and you use all positions in those alignments to extract the probabilities. The Deof pair, there was a couple, they're still married, even after, you know, doing alignments, making matrices together, you know. I couldn't imagine they still do, but they are still married. Anyway, so it's 92, but they're still there together. Basically, they use the blocks, a specially created database of many more alignments, of course, than Deof, but they used parts of the alignment rather than all of the alignments. So, one thing against, it's less complicated than Deof because they don't do any business with extrapolations. They take it immediately from the dataset. How do they do it? But it's a series as well. Here's the blocks database, very schematically, of course. So this is an alignment using another database called ProSite. I don't know if you've seen it. You could Google it up, find out what it is. That's a database that holds functional elements of protein sequences. So a block is something that matters functionally. And the Deofs argued like, okay, if you have sort of regions of a protein sequence that don't matter so much, neutrality regions here, then, you know, you could look at these alignments, but they don't tell you so much. You would look like to focus on alignments that functionally matter. If you do this, then your fitness is disturbed. That's meaningful. So they said, okay, we use these regions only, these blocks of the alignment, and that's why the database is called blocks. And now basically the trick is, if this could be a sequence, you know, and this functional amino acid is very often conserved. This might be a total A position. Is that very helpful? If you have only A positions, then you don't have differences, it becomes hard. So basically, what they say, they extract for their series of matrices, they look at these blocks, and they look at what kind of sequences are what similarity do they have? It could be that this position, for example, consists of sequences that are only 30% similar. There are many different letters, only 30% overall similarity. And here might be a position that is 62% similar. 62, you know, the amino acid score like that. Similarity number. So they select, they all the time for any series, for any matrix in a series, they select those columns that conform to what they need. Now, so basically then, here you go. The Blossom 62 is a matrix where all columns have at least a 62% sequence identity. Right? And this means that if you have a larger number in, already can tell you that, a larger number means a more similar matrix. And how is this for Dayhoff? A larger number means what? Longer evolutionary time. What do you expect with the probability? Smaller ones. Okay. But no extrapolations are being made like in Dayhoff. So how we calculate? Let's do a simple thing. Here's an alignment again. They don't use any trees. Very simple. Now, who can sort of see why these numbers are what they are? These are 5 columns, right? So these numbers are the 5 columns. Am I right? 3, 5, 1, 2, 3, 4, 5. Yeah, I'm right. So, why is NPP in the first column 1? Do you see that? How many do you observe? PP. Yeah, well, now, why is this? Why are there 6 observations of A to A in the third column? That's that number 6. It's a total A column. You see that? Why is that 6? This formula. You have A to A, 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 A to A. All combinations. That's this formula, right? N times N minus 1 divided by 2. I think we've covered that before. Somewhere. So, you have an alignment. Immediately you extract all of those mutations from it. You fill in your matrix. And here you go. And now check again. What do you think? Exact same trick. This should have been 7. If you add it up. And because you make them, as they did, you make them symmetrical, you double the values of it, just like before. Okay? So this is one of the base methods. We're nearly done now. It's amazing. Look, you immediately can calculate the probabilities, the frequency of those things. Here are the frequencies. This is just dividing the number in a cell by the total sum over the matrix. That's this. These are the numbers. That's what they also did, by the way. And then you calculate these numbers and so here, this is the mutatability. Here you have the frequency. You take the ratio. Here you see the old formula again, the real model. Takes it from the matrix, the frequencies. They take the log, the 2 log here, 2 times the log 2, and this is their matrix. Done. 2 steps to calculate, bang. So no backtracking like they did or to extract ancestral sequences and so on. Nothing like this, very simple. 2 steps. From counting, filling in the matrix, doubling the diagonal, calculating, normalizing what is the mutability, here you go, frequency, and the ratio. That's it. You're home very quickly. That's the matrix. So this is again in the same way as they did the base number, before taking the logarithm, again times 1000 now. You see the numbers are quite a bit different, nothing really is close to 1000. This one is very, and then here's then the final Blossom matrix as you probably use it in your algorithm sometime. And you see what was 17 before is not 17 now, and what was 2 before is not 2 now. So you see this matrix is using another data set, but it's also different. And the idea is that basically this matrix is more conservative relative compared to Pan 250. This tends, more amino acids tend to remain the same with this model. Okay, again, what does it mean? I told you this, positive for really similar, 0 for no difference between random and the real model. And another thing, of course, is what happens. There are 2 ways to influence your number if you look at this score. How can you become large with this number? I'll tell you, Pij should become big. One way. What's another way to become large? Pi or Pj becoming small. What are these? The frequency. Meaning, if you have a low frequency amino acids, chances are that they, because any observation on it blows up, right? Oh, you know, I expect very little. I see something. That's meaningful. I expect very much. I see a bit more. It's even less, still less meaningful. So, that's rare amino acids get higher weights according to the formula. Okay. Now, we're going to compare pen versus blossom now, based on an explicit with trees, you remember. This is just very empirical frequencies. This is derived from a very small handwritten data set. This is much larger, all with computers. Even in the 90s there were already computers. Higher pen numbers detect more remote sequences, more evolutionary time, more mutations. A higher number is, so a lower number then is more remote. The higher the number, the fewer the mutations. This is one little problem in blossom. Suppose there is a little error in the span1 matrix as we saw. What happens with that if we do 1,000 self-multiplications? It blows up. So they really scaled up the error propagation, you call it, right? And here, no such error because there is no extrapolation. The data set can be incorrect, but you take the data for any blossom matrix in the series directly from the data. You select your columns, and that gives you the matrix directly. Okay? Here, this is one scoring. This is called entropy. All the numbers, all matrices get a single score, and then you can put all the matrices on a single line compared to the scores. And there you see, so this is really one column. This is under there. And then you see that the pen to 50 is close, roughly to blossom 45. You see that? And blossom 62 is sort of, the next one in the row is pen 160. See that? So blossom 62 is more conservative than blossom 45. The lower the number, the more happens in the blossom series. Okay? Now, I'm heading off. So, this is my castle wall story, okay? This is evolutionary starting yesterday. We have a common ancestor. There are now two species, cows and horses, but they split off from one another only for one day. What do we expect about their sequences? A lot of mutations over one day. Even in the neutral model can't be that many. So let's say nothing happened yet. That means that if you would fill a matrix under that model, you would have only the diagonal values up because there is no mutation yet. Now we go to self-multiplications in the day of model and we wait, 4 billion years. What happens with the ball? What happens with old balls? Have you ever seen old balls? They corrode, right? The bricks fall off. This is what starts happening. Look, the ball is hardly recognizable anymore here. Yeah? What happens, you think, if you make, I don't know why you ever want to do this, if you make a pen 10,000 matrix? 10,000 self-multiplications, what do you get, you think? Or 1 million? Where does this go to?
Chaos.
Huh? Chaos. Absolutely. That's a good answer. But a bit more. You go to completely the random situation in the end. You multiply the signal away. The students are waiting again. So let's quickly try and finish with some philosophy. What did Dayov have? She wanted. What do you need to make an alignment? Is it fair to say you need a blossom matrix to fill in and calculate your alignment? The answer is yes. Then my next question to you is, what do you need to make a blossom matrix? You've seen it. You need an alignment. Oops! We have a philosophical problem. And there again, when philosophers say, what is the circular reasoning? Biologists say, now it becomes interesting. Because we have a feedback loop. This is what we have. There are a lot of biological, physical processes that do this. Anyway, that's important to know. In practice, what is your best alignment? What is your best matrix? There are no plain rules. Try stuff. That's basically important to know. Should I fill you in on this one? Okay, that will be the last thing I'll tell you. Promise, I know. So basically this was a study, and the only thing I'm showing is this was, we have alignments we know that are known to be correct from structure. I'm showing you one other paper, right? Here is, we make an alignment, and here is the percent identical residues. Here we take those sequences, where we know the alignment here, and we realign them, but with the best possible blossom series or whatever we have, the best possible semi-global, global, doesn't matter, we give it the best score. So this is the best you could make aligning those sequences. Look what happens. This is called the twilight zone in biology. 15 to 25% sequence identity is the region where there is very often a biological relationship still, but at this distance, right? 80% different or something. Look at the correctness. How correct are those? Not even half is correct here. Alignments make a lot of errors. And hopefully you make errors in the unimportant corners of life, right? If you make errors, make them in the proper place. So alignment is not easy. We need to better our algorithms. Hopefully you're going to do this. You're going to have a cracking algorithm in the end. Better than we would ever have expected. So I can tell you a lot more, but I told you not to do that. So that's it.